All right. Hi, everyone. Welcome to our 34th session of the MedAI Group Exchange. This week, we have Mike Wu from Stanford here with us to present his research on optimizing for interpretability in deep learning. Mike is a fifth-year PhD student in computer science at Stanford University, advised by Prof. Goodman. His primary research interests are in deep generative models and unsupervised learning algorithms, often with applications to education and healthcare data. Prior to Stanford, Mike was a research engineer at Facebook's Applied Machine Learning Group. Mike's research has been awarded 2 Best Paper Awards at AAAI and education data mining, as well as featured in the New York Times. So thank you very much, Mike, for joining us today. Before we start, could you let us know your preference on how you want to take in questions?
Oh yeah, feel free to just interrupt.
All right.
Yeah.
Yeah, and as always, let's always try to make this session as interactive as possible. Without further ado, let me hand it over to Mike.
Cool. Well, thanks everyone. I'm happy to be here and hope to share some work. This is some stuff that I worked on before I actually started my PhD with Finale Velez at Harvard, and we've done a few follow-ups. So this will be like a summary of all of that direction. And the main question here is just to see how we can make deep neural networks interpretable and how they can be useful for some clinical applications. Okay, so to motivate the problem a little bit, something we hear a lot about is that like deep learning is a black box system. And for like many years, one of the big goals of deep systems was to be highly performant. But now I think a secondary goal that's becoming more popular as these systems get used in practice is that deep learning has to be explainable. Several applications come to mind immediately when we think about interpretability. For example, something like self-driving cars. We want to know like why an accident happened, and we want to have guarantees that something like that won't happen again. And Finale in particular thinks a lot about applications of AI in law and medicine. So for example, where we're making predictions about the likelihood of recidivism or whether we should give a particular drug at a particular time. And these kind of decisions just can't be black box. Like we as human experts must be able to audit or adjust the rationale behind models that are making predictions for these. So then the question is, what does it actually mean to be interpretable? So I think like unlike most terms that we use in machine learning, this actually isn't that well defined. So we can look at a few examples. I think that's the best way to explain how we think about interpretability. And some of these might be a little outdated, so please forgive me if I'm missing any of the latest methods. But one simple thing you can do is visualize feature maps. So imagine taking any input example, and you can compute the output of an intermediate layer. So for vision, this is often a convolutional activation. And we can maybe even average over these across many images of the same class and visualize what we think is being captured at that layer. And if we stare at these pretty pictures, some of them are reminiscent of features of the objects themselves, like in orange. Or we could look at gradients. So for example, a rather famous method called GradCam says, try to find out which pixels are responsible for motivating the network to make a particular prediction. So here we can see like the dog's face, but also maybe the cat's body is making it detect these particular objects. Other ones are more focused on input-output analysis. So LIME is also another very successful method that learns a linear local approximation to a deep nonlinear method. So like suppose you have some crazy decision function, well at a fixed point, you can approximate the behavior linearly. And then this is nice because we can look at the weights of our linear model to get a sense of what the model's logic is. And finally, we have a lot of methods that try to use deep learning to explain deep learning. So this is like producing like text explanations to why a model did something, or trying to distill a large neural network into a smaller one. So there's lots of different things, and they can get quite sophisticated. But pausing here, I kind of just want to take a step back and observe that like one of the things a lot of these interpretability methods share is that they're really good at answering why did we predict X for this specific example. And that's important because when a model makes a mistake, we want to understand why that is. But in the context of greater things, there are lots of things that I really want to answer, right? Like I might want to know what the behavior of a model as a whole is, or I want to know what sources of bias have I accidentally put in, either from the data set or my design. And also I care about how do I repair or improve my model's performance for next time. And so in other words, I don't really just care about why a model got a single example wrong. Being a human in the loop or working with models in practice, I really want to sanity check the model's actual computation and make sure it passes my own bar before I deploy it into the real world. So I think one way to put this is that while interpretability is a rather vague idea, we propose to actually study a more careful definition called being human simulatable. So that means that you as a human can look at all the inputs to your model, look at the model parameters, and walk through all of the steps you need to make the same prediction as the model did. Right? But the caveat is that you have to do this in a reasonable amount of time. So if I give you a deep learning network, you can't just do a bunch of matrix multiplications by hand. That doesn't count. So for example, something like a linear model or decision tree, they're simulatable because I can easily look at it and be like, this is why it said this particular thing. So we can look at some of the prior methods we talked about and ask if they are simulatable. And mostly that answer is no, which makes sense because I'm imposing a stricter definition than what these papers were working with. But just for exposition, like for example, let's focus on like GradCam in the bottom left. Knowing which pixels are used doesn't tell me how the model is actually using it, so it doesn't satisfy that criterion for me. NLP explanations on the right-hand side are a little closer, but it still feels loose with like a very few guarantees. It's not clear if these explanations are really tied to model behavior. And finally, Lime is kind of interesting in the upper right, because it is rather simulatable. Certainly, if we focus on a single data point, if the linear approximation is good to the true function underneath, which it usually is because it's local, we can step through the logic of the linear model to make a prediction. And in this case, I can reason about a lot of things. Like I can reason that maybe we didn't predict flu for this patient because they didn't experience fatigue. So are we done? Is Lime the end all be all? And I think no, because we still want more. And what I mean by that is that Lime is a nice local approximation, but I want something that's global in general. I want something to tell me what the model is doing as a whole, not just why I made this particular prediction. So a simple thing you might say is, why don't we just extend Lime to the model? Let's just try to approximate a deep neural network into an interpretable one via distillation. So let's just put it into a linear model or a decision tree or logical rules. But the problem is that this will probably do very poorly on the actual classification or prediction task, because otherwise, why are we using a deep neural network in the first place? So that's the context, that's the setup. Now we're going to get to the punchline of the work, which is that instead of trying to understand models after training, we want to take a different approach, which is I want to optimize for interpretability while I'm still learning the model. So that's a fundamental distinction. I think most works treat interpretability as something you do after you have a fixed trained model, but this feels like an ill-posed problem in the sense that there is no incentive for a neural network to be simple. Even if you try to impose sparsity, that doesn't necessarily imply simplicity. And we're training these things to be highly performant on very complex tasks, which means, of course, it has to learn something very complex. So if we're going to try to impose constraints about interpretability or explainability after learning, when we don't have control over the weights, that seems like a very difficult problem. Maybe it's something that we can think of while we do have some influence over the parameters. Okay, so the intuition is that I want to treat interpretability or simulatability as a regularizer term in my objective. I want to penalize my network for being really hard to simulate while we're still training. So in your head, you might think like we have this weird landscape that's very complex of all the minima that my neural network could achieve. And some of them are going to be highly performing. And traditionally, we use stochastic gradient descent to find those, and that does a pretty good job. But of the high performing ones, some of them are more simulatable than others. That's very likely true. And so how do we find those minima that are both simulatable and highly performing? And in some sense, I'm willing to trade a little bit of my performance if it means I can be more easily understood. So this is very reminiscent of classical regularization techniques like L1 or L2. But here we're not really optimizing for some nice property of the weights. We're optimizing that the weights lead to a model that is easy to simulate. Okay, so that's the main premise. But the big question you probably have in your head is, well, how do you do that? What is the regularizer for simulatability? And so the approach we introduce is called tree regularization. So as the name suggests, we're going to be working a lot with decision trees. And why does that seem like a good option? The rationale is that they're very easy to simulate, right? If I give you a decision tree like this thing on the right-hand side, you can step through it one decision node at a time to check what the model is doing. But also, unlike linear models, you can capture nonlinear decision boundaries. So a property with decision trees is that you can compute something called path length for a prediction made. So suppose I give you an input X and you drop it down the tree, so it falls somewhere to a leaf node. The path length is then the number of decision nodes or internal nodes that it had to reach to get to its leaf node. So here I have some random decision tree from Google. And suppose that for my input, I reach the decision node age on the right-hand side. That means that I had to touch 4 internal nodes along the way, giving me a path length of 4. So if I give you a whole data set, I can compute the path length for every single example. And the average over those, I call average path length. And the notion you should have in your head now is that average path length is a measure of how complex my decision function is, right? If I have a larger tree that's very long, that means that it learned a very complex thing. It had a lot of edge cases to cover to capture some true decision function. Whereas a short one is very simple. Okay, so the problem setup for tree regularization is that we are in the classic supervised setting. So we have some data set that's labeled with inputs X and outputs Y. And we have a neural network F with some parameters theta. And we're optimizing a traditional loss. So for example, if we're doing classification, then we optimize cross entropy, but we add this extra regularization term, omega, that takes as input the weights of the original model theta. So you can think about this as an L2 norm, for example, and that's classically done. But instead, what we do for tree regularization, the main idea is I want to set the regularizer to be the average path length of a distilled decision tree. So one thing to bear in mind is that this distilled decision tree is not responsible for approximating the final network, but the current network with whatever its weights are and whatever epoch it's at. The role of the decision tree is to approximate that. Then given that decision tree, I'm going to compute the average path length over all my training examples. And that'll give me a notion of how complex this decision tree is, which I treat as a notion of how complex the original neural network is. Cool. And I hope it's clear why I chose this as a proxy for optimizing for simulatability. Because if the regularization term here is very large, that means that we needed a very large decision tree to approximate the neural network faithfully. That means whatever the neural network learned is very complex. But if the regularization term is small, we don't, meaning that the neural network has a very simple decision function that only needed a few nodes for the decision tree to represent well. And another way to think about how its relationship to simulatability is that every additional increase in path length is an additional thing that I have to think about as a human to understand what the model is doing. right? If I walk down a decision tree, if you add me a decision node, I have to input extra costs to think about what it's doing. So a larger path length would mean that it's more costly for me to simulate as a human. Okay, so this is nice. I wish we were done here, but we're not. And the big issue is that, well, this thing isn't differentiable, right? If you think about what you have to do, you have to take your neural network's parameters and then train a decision tree, which is a non-differentiable function. It requires a lot of discrete choices. So instead of directly optimizing this term, what we do is we have to introduce a surrogate neural network. And this is often a small one, but the role of the surrogate neural network is to learn a mapping from the parameters of the original neural network theta to the average path length. I can just treat average path length as a continuous label. So what exactly does that mean? Let's step through it a bit. The first step is that I have my main neural network with parameters theta, and I'm taking gradient steps on it. And every gradient step, I get a new theta value, right? And I store that away. And for every theta value, what I do is that I train a decision tree to approximate the predictions made by that model at that theta parameter value. So yeah, and then given that decision tree, I compute the average path length of it, a measure of complexity, using my training set. So every gradient step, I'm getting one set of weights from my original model, and I'm getting a decision tree that I use to compute average path length. So a measure of complexity of this particular model weight. And I have lots of these tuples, right? Because I'm taking lots of gradient steps. So I'm somehow generating my own data set here with labels. And this part is fine, doesn't have to be differentiable because I'm not going to compute gradients through computing the average path length here. But what I do use this data set for now is that I optimize a surrogate neural network to predict the label from the original model parameters as best as it can. This is the main idea. So I just want to walk through it again pictorially. And so there's 4 steps total to tree regularization. The first one is just that, we start with some data set, X and Y. We have some complex model. This could be, something like a LSTM or a large network, MLP or something like that. And it makes predictions, Y hat. And given a collection of predictions that it makes, I can use that to train a decision tree. And given a decision tree, I can look again at the training data set, and I can look at the path lengths required to make all those predictions and get an average path length. That's step 2. And now at this point, I have a tuple that I can store away. I have the original weights of my model at this step theta, and I have the average path length that I just computed. So after a few gradient steps, I'm ready to train my surrogate network. And J is some hyperparameter you tune. But now I just train my surrogate network using that data set I collected. And now I have a deterministic differentiable function from original model's weights to average path length prediction. And I plop that into my regularization term. I don't optimize the gradients of the surrogate network when I'm optimizing my original network. I just treat it as a fixed deterministic function. And then I just loop. And one thing that happens is that the surrogate will grow kind of stale. So every J steps, you might want to refit the surrogate. But what we find in practice is that the surrogate doesn't need to be a big network. This transform is actually not so hard to learn, surprisingly. So we just replace the regularization term every now and then to refresh the quality of the surrogate, and we optimize the main model that way. So this is the main idea. For the rest of the talk, we'll be like building intuition, some extensions and experiments in a clinical setting, but I just want to pause here for a second and see if there are any questions. But if not, I'm happy to continue. Cool. Let's move on. And of course, like if you have questions that jump to mind, please just interrupt.
So Mike, one quick question. So do you have any restriction on your decision tree or no? You let it grow as big as possible?
Yeah, so at first I thought I needed to have a restraint, like you can only have this max number of nodes or max number of examples have to be there per leaf. Um, you don't need to, but I find that if you do set some of those to be reasonable upper bounds,
Right.
the training is much more stable.
Yeah, because I was mainly curious that since we are using like this very huge data set for training, so how you constrain your decision tree growing, like do you have a like restriction on the depth mainly? Because path is like one of your important, path length is
Yeah.
one of your important variable.
So I don't restrict depth explicitly. The one thing I did set in my experiments was the minimum samples per leaf.
Okay.
It'd be, yeah, some upper bound. Yeah. Cool. Oh, and I do, sorry, I forgot. The most important thing is I prune my tree because I don't want redundant branches. That doesn't count, right?
Okay.
Like if I start having extra nodes that actually make the same decision as my previous node because I didn't constrain my tree, that's problematic.
Okay.
Because I really care about the minimum tree that's required to model my neural network.
Exactly.
So what I do is I just do pruning.
Okay. I think Varun has a question in chat.
Cool. How do we know that some points are more simulatable than others? Do you mind providing some more context? What are points?
Sorry. So when you showed the objective function with different possible solutions, you mentioned that some of them are more simulatable than others, and we want to get to those solutions. Meaning those optimal points.
Yeah, I don't think I have a proof that's what you're looking for. It's more intuition. Like, for example, like one thing we do know is that like sometimes having like increasing the complexity of your decision function might not increase your performance on downstream tasks. So for example, like suppose I have like a very easy task that's just a linear division. So I can do that. Or I can make a really wobbly line that's roughly a linear division. Both of those perform, let's say, equally on some transfer task, but one of them is very unsimulatable, whereas the other one is very simulatable. So I don't have a proof, but I think it's easy to come up in your head with like things that are around equal performance, but perhaps one is a lot less simulatable than the other.
I think there's another question in the chat.
Got it. Thanks.
What's the criteria you are using for decisions?
What is a decision? You mean a decision in the tree?
Yes.
So you have your input features, and you train cart. I train a decision tree via cart to minimize some objective. In fact, easily said, I just use the sklearn implementations. So I don't manually decide those decisions, if that's the question.
So like the criteria is like the entropy you're trying to calculate, the scikit-learn feature which it already holds the default parameter value.
Yeah.
Okay. All right. Thank you.
Yeah. So you have, this is a supervised task for the decision tree.
Yes.
No, I think what Sandeep wanted to ask you is that, Mike, that if it is entropy based or is any other criteria, optimization criteria used?
I see. I tried both in sklearn, so I think it was Ginny based and entropy based.
Entropy, yeah.
They roughly are the same. So I don't think it really mattered. Yeah. The tuning parameters might be a little different, but I think it should be roughly the same.
And I guess I have one last question, sorry.
Yeah.
So I guess how do you, based on just the random seeds of the random forest, like the decision points or I guess trees can be very different. So how do you, like, I guess like normalize or like find a uniform point?
Yeah, great question. So if I understand the question, you're saying that like if I train a decision tree multiple times on the same set, it can be very different.
Yeah.
Yeah, great question. So I had to remove something from the default sklearn implementation that bugged me a lot because it wasn't working at the beginning, which is that they randomly choose a subset of features to train on. Okay, so there's like easy variance to capture and there's hard variance to capture. And there are some things you can do about hard variance, such as pruning was one of them. That was huge. So great question. And then the second one was making sure you're training on the same feature set. Otherwise, you're clearly going to get different decision trees. The small variance in between training trees every now and then is okay because you get to see a huge data set. So I think the error kind of just amortizes out. I mean, ideally we wouldn't have this error, but I didn't find that to be a big issue in practice.
Okay. All right. Thank you.
Cool. Great. Thanks for the questions. So next I want to just talk about a toy example to build some intuition, because what is tree regularization? I think pictorially we should go over it. So here is a data set where the black line in the middle is the true decision function that I just made. It's a parabola. And I then define two other parabolas where I flip some labels in between them, just to incur some noise. So this is not a trivial task. And you want to incur some noise so that there's overfitting. And then the task is just to separate the two labels. And what we're going to do is try a few different regularization methods like L1, L2, and tree, and try them at different strengths and visualize the decision boundary that's learned. So for L1 and L2, perhaps you get somewhat not surprising results. You start with very complex objectives if you overfit appropriately. And then what happens is that as you increase the regularization strength, you'll get simpler and simpler decision boundaries. For L2, you get this nice parabolic shape. The L1 looks a bit more sharp, which you might expect. And eventually they just collapse to a line, which is nice, which is what we expect. When we do the tree regularization, same thing happens. It starts with something very complex. But the interesting behavior is that if you start regularizing more, it becomes axis aligned. And that makes sense because the more you regularize, the more you're encouraging the model to be like a decision tree. And a decision tree is axis aligned, right? It'll be like if the X point is above -5 and below -5, then do something, the Y is, yeah. Eventually, and it can toggle between different axis aligned decision functions. I mean, in practice for like real world data sets, you probably won't get axis alignment because you'll be regularizing very strongly. And at that point, you might as well train a decision tree. But the point here is to show that like you can interpolate between this axis aligned decision function and a smooth high dimensional decision function nicely using tree reg. Cool. So that's the main tree regularization idea. Before I present results, I just wanted to go over a small improvement we made in 2019, which is to model context dependency. So the intuition here is that tree regularization is an example of global interpretability, right? I want my model to be simple as a whole, whereas Lime is an example of local interpretability. I want my model to be simple at a point. I think talking with practitioners, and maybe in the clinical setting in particular, the true desired is somewhere in between. And so global simulatability is nice, but probably unrealistic in a lot of settings because there's many different contexts in real world applications. So for example, a physician's logical reasoning is probably very different in the emergency room than in regular practice or during surgery. And if we only regularized for global simulatability over all these contexts, we might not capture one of these particular segments, or we might just completely ignore them and bias towards the more complicated settings. And so the point is quite simple, is if you know these contexts up front, which you often do in expert domains, then we would like to impose these priors in our regularization directly. So more concretely, what that means that is we suppose access to a few partitions of our domain, R1 through RK. So these don't have to be complete partitions, nor do they have to be disjoint. But for simplicity, let's assume they are. And these are supposed to represent expert knowledge. So for example, a physician might tell you a heuristic they used to identify an action to take. Or a driver might tell you that they behave very differently under harsh weather conditions versus easy weather conditions. And worst case, if you don't have any expert knowledge, you can always try statistical clustering or unsupervised methods on your machine learning data set and impose regions that way. But the simple extension of tree regularization is to penalize the largest region at any point in time. So instead of just treating the average path length as a regularization, I separately train a decision tree for every single region upfront, and I penalize the maximum. And I think a good question might be, why not penalize the sum instead of the max? The sum seems the most reasonable. And that's certainly what we started with as well. But what we noticed was a failure mode where we over penalize the simpler regions to basically trivial functions first before the large regions are penalized. And I think the intuition is that it's a lot easier to penalize simpler decision functions to be simpler even than hard ones to be relatively simple. So yeah, small subnote, that's why we choose max. And so another toy example to build some intuition to compare these different kinds of interpretability is that suppose this is our true decision function. It's some like jagged line where the red points and the green points represent two classes. Then a globally simple or globally simulatable decision function might look something like this. Right? It's very easy to understand, but it might not be the most accurate. Whereas a locally simulatable function might look like this. Around every point is very simple. It is always linear. But in totality, it is actually more complex than the true decision function. And the regional one, if we knew the regions up front, suppose they are these like shaded regions, might find a happy medium. Now, this is a trivial example. I don't mean to suggest that regional will find the true one always, but the intuition is that like, if you know some information up front, you can probably achieve better minima that trades off between performance and simulatability than if you just tried the global approach. Okay, then we applied this method to some applications in clinical decision making. And what we focus on is predicting when to prescribe medication. So we're given features of a patient, and this could be like lab results or vital signs, things like that at every time step. And what we want to decide is this a moment that we should apply some sort of medication? And the labels here are what doctors actually did. And so I'm sure you guys are much more familiar than this data set than I am, but we use the MIMIC 3 data set, which just covers patients in the intensive care unit. And the labels here that we study are whether physicians decided to use a vasopressor or a ventilator, things of that nature. And one of the first things we did is, spoke with clinicians and asked about different contexts that they might think about things in. So two things they suggested were splitting by care unit. So patients in the surgical ICU and patients in the medical ICU might receive different kinds of decision functions. And the other one is splitting by summary statistics that naturally clustered patients like SOFA. Okay, so then the evaluation metric that we care about is one, we care about highly performant models, right? And by that we can measure something like area under the curve. It's a binary classification task. It's just every time step, are we giving yes or no? And the second thing we care about is being simulatable. And beyond using average path length as a regularization term, here we also use it as a metric to compute simulatability. I don't actually care about the raw values that much, but things like, suppose I give you a model that's frozen, I can train a decision tree to approximate it as best I can and compute the average path length. And again, bigger average path length should mean a more complex model function. So I can also use average path length as my measure of simulatability. Yeah. So we make these plots. These plots are on the y-axis, we have performance, and on the x-axis, we have the difficulty of simulation. And what we want to be is we want to find these nice concave functions that really touch the upper left-hand side. we really want to find minima that are highly performing. So high on the y-axis, but also low on the x-axis because they're easy to simulate. Things that are very much to the right-hand side are just overfitting. Okay, so I'm going to show you a dense slide. Sorry about this up front, but this is basically the main results. Each of these plots are basically on this scale. So let's go over one of them. So again, the x-axis here is average path length, simulatability, and the y-axis here is performance, so the area under the curve on a test set. And every point represents a model. Every line represents a model family. So all the light blue lines are all regional decision trees. All the red lines are decision trees. And what we do is we toggle some parameter that controls the complexity of models. So for neural networks that are regularized, like for example, the yellow line is L2 regularized neural networks, we just toggle the regularization strength. For decision tree, I believe we toggled the max depth or something like that. I don't really remember, but it's some parameter controlling the size of the tree. And what we care about is we care about curves that touch that upper left that are more concave. Okay, so a regional decision tree is a baseline that we did that says use the a priori regions and train a decision tree in every region. Like if that did as well as our regularized model, then there's nothing for us to do. We shouldn't regularize a notebook. Okay, so some things to point out. One is that global tree, so if you ignore the pink lines, global tree does pretty well in the sense that like it seems to be mostly strictly dominant to something like L2. But what you see is that L2 and global tree, they don't find very many minima that are at very low average path lengths, right? They seem to start out really nice and then they just end. Whereas our baselines like decision tree can find very minima, lots of minima across the entire APL spectrum. And the reasoning here is global tree is very sensitive where if you start regularizing a little too much, at some point past the threshold, it'll collapse to zero, basically learn the trivial function. And it's really hard to search for meaningful minima there. It's just gradient descent is tough. But the main benefit of why we were interested in regional tree was the hypothesis that that wouldn't be true if we already divvy it up into easier subproblems. And regional tree, we have 3 variants. We have 3 variants, all in pink. And what we see is that, yes, it's nice that it's like also dominant to global tree, even in the high APL region, which is nice to see. But what's really more important is that it finds a lot more minima that are in this low APL region that do decently on AUC. Yeah, that's the main point. Cool. Then we did a second data set. Actually, Sonali, one of our co-authors, conducted this, where she has this access to this data set with treatments for HIV, and we did a similar analysis, and the results are roughly similar. Oh, and I should add that like it makes sense that all these plots converge to an upper right point, right? Because with minimum regularization, they should all reach the same minimum subject to noise. Cool, and then the black dot here that might be in the old plots too represents no regularization. And it's pretty low because without any regularization, you kind of find poor minima in these settings. Okay, and then I think a cool side product of this work is that you did all this hard work to distill your neural network throughout the entire way of training. But of course, you get a distilled decision tree at the end of the day. And so we are still, of course, approximating the neural network with a tree. So for regional tree regularization, we actually have a tree for every region we're in. And so for our data sets, we can ask clinicians to look at these trees and see if they make any sense. And so here's some examples of very simple trees I found. So these I took from some of these minima here in the middle, where it's like Not the best AUC, but decently well. But it's a very low average path length. And so it really only captures like 1 or 2 or 3 decision points. There are larger ones, but harder to visualize. And so what we got from feedback was both positives and negatives. So the positives are like, yes, it passes some sanity checks that the appropriate feature is being used that we use in practice to decide something. But then they can also make requests that's like this feature, such as oxygen level, should have appeared higher in the tree, should have been like a critical node, and it wasn't. And so I think that kind of reasoning is the hope for this direction of optimizing for interpretability. Whereas like if I give you GradCam or some method for a computer vision problem, what you can kind of see is, oh, it didn't do the right thing, but you're not able to make requests about what should have happened or how reasonable the model's logic really is. And I think like the hope of this direction with decision trees is that it enables this kind of two-way interaction between the model and an expert. Cool. And as with anything, there are limitations to this method, so we should be cognizant of them. The first one is that this is not as easy to train as a vanilla stochastic gradient descent model, right? These days, if you're doing a classification task with a big neural net and you don't care about interpretability or regularization, you can just use Atom or something and it's pretty good. This is not that. It takes some work to find stability. That doesn't mean you're going to like crash every time, but what it means is that you have to do grid searches over regularization weights. Hence why I did those large plots of curves. We asked, great question, 1 second. We introduced some tricks in the paper, but this is still an art, as is gradient descent, but this is more of an art, I guess. Second is that regional tree regularization requires knowledge of regions. I think it's most useful when you have some a priori information. We want to be explicit about that. We do not automatically derive regions. We tried some experiments on like UCI datasets using clustering algorithms, and they worked decently well, but we don't expect them to work more generally for real world applications. And lastly is that there is a computational cost, right? I have to train decision trees all the time, and evaluating average path lengths is cheap, but not free. So I don't remember exactly how much time it costs. It's in the paper, but it is a factor. It's not like plus 10 seconds. It's like 5x, 3x, something like that. It's a decent amount of time. You can, of course, parallelize decision tree training across regions. And you can, of course, also ask other worker nodes to implicitly train your surrogate networks. But all this is a lot of engineering. And at the base point, it takes a lot of computational work. And finally, I don't think this method is applicable to a lot of modern machine learning settings. So for example, like computer vision, natural language, maybe not natural language, computer vision at very least, how are you going to model that as a decision tree? Will it be over pixels? That's tough. So this is definitely assumes that the features themselves are interpretable, as is the case in medical clinical settings, but not always the case in a lot of machine learning. Okay, and the final thing I wanted to touch on is just some cool extensions that I found building these slides since I visited this. The first one also came from Finale's lab, but I wasn't super familiar, is that you can do gradient regularization. So decision trees aren't the only avenue for interpretability. You can have lots of other ones that you think are better or worse. So one particular notion of interpretable is that some statistic of the gradients is simple. And this one is nice. You probably don't need a surrogate that much, but you can just replace that regularization term with another notion. And if you need it to be differentiable, you can use the surrogate trick. So it doesn't have to be decision trees. And the second one is that for our final journal submission, we added some simple computer vision tasks just to see like how far we can do. I'm not very bullish on this direction, but there is some promise here, which is that what if I like am inspired by like the bounding box detection architectures? I take random boxes as features in the image, right? And these boxes are of different sizes. and I treat those as my inputs. And then the decision tree basically is responsible for choosing which segment is the most useful for making a classification decision. And we can then do the same tree reg thing on this. And what we get is on this right-hand side is we can just visualize which boxes in our image were the most important. And increasingly, as we increase regularization strength, as the row goes down, so the first row is like low regularization strength, so you can see it's like looking everywhere. And at the last point, it's high regularization strength. So it's really only looking at things it finds critical. Like, this is not a perfect notion of interpretability. You can argue that it might not even be that simulatable, but it's some step towards applying this algorithm to unstructured input domains. Cool. That's it. Yeah, thank you guys for listening. If you have any questions, I'm happy to talk more. But otherwise, I think that's everything.
Great. Thanks, Mike, for the talk. And I think there is already one question in the chat. Varun, do you want to unmute and ask a question?
Oh, I think he said he couldn't speak.
Oh,
but
yes.
Yeah. I tried to answer this question, but actually give me 1 sec. I can actually look up how much it costs. It is in the paper.
Yeah, so Mike mentioned it's like 2 to 3 times more than the original training or without the tree regularization. Meanwhile,
Okay.
Is there any other question from other audience? Sorry, Mike, go ahead.
It's about a factor of 2 to 3. If that helps.
Mm-hmm.
Yeah. It's definitely dependent on your architecture.
Right. Is there any other questions from the audience? Yeah, I actually have one question. So you mentioned about a clinician look at the interpretations and they think that one particular node should be a more important node, but it was not. It wasn't. So is it possible to actually encode this type of like expert knowledge in the tree regularization?
Yeah, that's a great question. We didn't take this step forward, but I think so, because like, what is regional tree regularization actually doing? It's very similar to imposing a root node, right? That first divides by region. I mean, it's not exactly that because we're doing max, not sum, but like if we were doing sum, that's exactly what it is, which means that if I can also impose the second node, like you can give me part of a subtree and I'll learn the rest. You can extend tree regularization to do that.
All right. Yeah. Thanks. Any other questions?
Yeah, Mike, I probably missed that point. So did you also evaluate the performance of your surrogate network at any point or no?
The performance in terms of how well it can capture. Yeah. So the way we trained the surrogate network was that it had to reach a minimum quality of. Yeah. So we don't set a fixed number of epochs. It just has to reach some accuracy level.
And what is your, like, do you have any observation, like what was the accuracy that surrogate network reached after which it can actually perform?
My observation is that's super easy to train surrogate networks, which is kind of wild because it doesn't sound like an easy transformation. Like going from high dimensional weights to average path lengths I thought it was gonna be really hard, but you can get away with like a 2-layer MLP. And yeah, because you have so much data. I think that's the saving grace, maybe. Like the data set of APL weights you can generate is massive. And so, and you can add to it arbitrarily, right? If you have 2 weights, you can take any convex combination of them and compute the APL. So you can enlarge and augment your data set infinitely if you want. And so given a large enough data set, a 2-layer MLP with some decent width seemed to like do it within 20 epochs. Well, I mean, that depends on how big your data set is, but for me, it really didn't take that much time.
Okay. So you just represent what So how did you represent your interpretation results to the clinician? So
I gave them the
you,
raw decision trees.
okay, and they were fine with it, right?
Yeah.
Okay. So you only did the experiments up to now on the tabular data, probably.
So the initial experiments were actually done on time series data set, but
Okay.
I didn't present them because they're harder to explain. But there we
Okay.
just have a LSTM and rather than a feed forward network.
Okay.
Yeah.
Okay, makes sense.
Any other questions? If not, let's give Mike a round of virtual applause. Thanks so much, Mike, for the talk. And yeah, thank you everyone for joining us and for the very fruitful discussions. We will upload the recording of this talk later to our YouTube channel. And if folks have further questions, feel free to reach out to us or leave your questions under the video of the YouTube. All right. Thanks, everyone.
Thank you, Mike. Bye.
Thanks, everyone.
Thank you.